the closed curve bounding your open surface. So in order to perform the loop integration here, like to move around this circle, the easiest approach is to use what is called polar coordinates. So what is polar coordinates here? In order to perform this loop integration here, we will employ polar coordinates. So what we are going to do is that here we are already on the XY plane. We will write a certain radius here, R, and we will define a theta here, R and theta. Okay. So if you take any point here, the X, by dropping this on the perpendicular on this X axis, this is your X. So your X here will be, if you follow trigonometry, this is 90 degree. This is your X. R is your, what is that? Hypotenuse. So X will be your R cos theta. And by dropping this point on the Y axis here, it will be like this. This is 90 degree. So this is your corresponding Y coordinates. Y coordinates here will be, if you follow this as a 90, this as your theta, and the this angle will be your another theta, right? So if you have two parallel lines like this, if you have two parallel lines this, and you have an intersection like this, if this angle is theta, this angle is also theta, alternate angles, right? So if this is theta, then your Y here will be R sine theta. So using this polar coordinates, instead of writing X and Y, you can write in terms of R and theta. Okay. So here in our particular problem here, we have a circle equation like this: x squared plus y squared equal to 1. The radius R is 1. So X is, by putting R equal to 1, X can be written as cos theta, Y can be written as sine theta, like this. R is 1. Okay. Now, what will be, say, your A dot dr? You know that instead of X, you can write cos theta. Instead of Y, you can write sine theta. What will be our dx? Dx is simply differentiation of X equal to R cos theta. Differentiation of X equal to R cos theta is dx upon d theta will be R into differentiation of cos theta is minus of sine theta, isn't it? So when you write dx will be equal to minus of R sine theta d theta. R value is 1. So simply your dx can be written as minus of sine theta d theta, just like this. Your dx is minus of sine theta d theta. Now instead of having your xy coordinate system, we have our r theta coordinate system, polar system. So when we write in terms of our r theta polar system, if you plan to go around this circle, if you want to move around this circle, what you have to do is, you know that this is your r, this is your theta. If you want to move this point by integration, means integrating over this closed curve, means you are summing over this closed curve. If you want to sum over this closed curve, you have to move this point around this circle. In order to move this point around this circle, what will be the limit for theta? See, the lowest value of theta is here, theta equal to 0. As you move around like this circle, this is, when you move to this point, your theta value will be 90 degree. And if when you move to this point here, your theta value will be 180 degree. And then eventually you can come around. So you can have a limit of theta from theta equal to 0 to 2 pi, 360 degree. So if I choose a limit of theta from 0 to 2 pi, then I can move the point along the circle using these polar coordinates. Okay, so if you follow that mathematical step, like I think everyone can perform the integration here, this is what you will get. And in order to integrate sine square theta, you have to use cos 2 theta formula, which is given here. Here cos 2 sine square theta will be 1 upon 2 into 1 upon 2 minus cos 2 theta. So I think you can follow the subsequent integration step. So that is quite simple. You will get, by putting the upper limit and the lower limit like this, finally you will get pi here. So the loop integration of a dot dr will be pi over the circle on the xy plane. This integration is over the circle on the xy plane. Now, in order to verify Stokes theorem, again we have to calculate the right hand side of this Stokes theorem, which is this. Okay, so first we will perform curl of A. This is simple, curl of A. You can use a determinant form here, I, J, K here. Curl is del upon del X, del upon del Y, del upon del Z. Your A vector is like the coefficient of your I cap is this, the coefficient of J cap is this, the coefficient of Z cap is, K cap is this. Then I think everybody knows how to take the determinant here, I cap into del of minus of y squares upon z upon del y minus del upon del z of minus of yz square, like this, if you follow. And here this and this will cancel out. Finally, this is what you get as curl of A. Curl of A here in this case will be simply k cap here, because minus into minus is plus here. Now the integrand here is, if you recall what we have seen here, we have to integrate this, isn't it? That is curl of A dot n cap ds vector. So if you take a dot product like this, what will be this quantity? This quantity will be simply like, let me draw it here to clarify my point here. So let's say you have a surface like this. You have a surface like this, for example. You have an inclined surface. And here in this case, the unit vector n cap of this surface, let's say there is a small ds vector here. Your ds vector will have unit vector like this. Ds vector will be thus ds into n cap. Ds is the actual infinitesimally small area. N cap is the vector or normal to the surface it represents, but along the outward direction. Outward unit normal vector. Okay. So you have a ds vector pointing like this, and this axis is your k cap or z axis. Okay, z axis direction, unit vector along the z axis is k cap. So when you take a dot product with k cap here, k cap dot ds vector will be what? Ds of, what is this angle here? Let's say theta, ds cos theta, isn't it? Ds cos theta. If theta is the angle between k cap and your unit vector n cap there. So what will this information give us is that, just 1 minute, I have one message here. Okay, so what this ds cos theta will give you is that it will give you the projection of this surface on the xy plane, something like this. Let's say this whole thing is your ds here, this is your xy plane, for example, Now when you write ds cos theta will be this. This will be your ds cos theta. This will be a projection of this inclined surface on the xy plane. A projection of this surface on the xy plane. Okay. So in our actual problem also, you have your xy plane here, and you have a half sphere like this, and over here your unit vector n cap will be outward unit normal to this. And if you take a ds vector here and there's a k cap here, if you take a dot product with this k cap here, this will be simply a projection of this inclined surface on the xy plane. Okay, and if you have another ds here, so what we are doing is we are dividing this spherical surface into a number of infinitesimally small area element. So each of this area element will be having a dot product with your k cap here. So when each of these area element is having a dot product with your k cap, this will simply give us a projection of this area element on the xy plane. And over here, if you have your ds vector will be pointing along this direction, or your unit vector in this case will be pointing along this direction. If you take a dot product with k cap here, this again is a projection of this surface on this xy plane. Okay, so if your ds vector is a projection of this ds vector, the actual curved surface on the xy plane, when you perform the surface integration or the surface integration here, it will simply give the area of this circle, isn't it? It will simply give the area of this circle, because when you are integrating over this whole surface here, that is when you are integrating the projection of ds vector on the xy plane, it will simply be the area of this circle. Okay, just a minute. Oh, hello, pa. In committee zomo. Ole, imo. Lo bolok lo mo, rema hi aron troy man chon rema ko ron ti ranga mo. Oh, cut le hal de Oh, hello, pa. Hello. 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 Lo halo ro so. Remai mu online class ka nei laglo ai ka lecture laglo view ka pa he kan committee zo aron tia I roi hana ya man lo so class ka ti to lo ngai ni me I thi ram so mo roi lo me la ka pa ka scooty zo ngai scooty zo can do zo ole along hang so so oh an zo begin ko ta lo ha ni zo begin ko ta ko kon committee ne bang che mo ole Okay, so what I was saying is that when you take k dot ds cap here, this is simply a projection of that unit vector on the xy plane. Projection of that unit vector on the xy plane will be as written here. This is the xy plane. So if you have what will be the infinitesimally small area here on the xy plane, this will be simply dy into dx. Your infinitesimally small area element on the xy plane will be dy into dx. Small increment along y multiplied by small increment along x, that is infinitesimally small increment along y and infinitesimally small increment along the x. If you multiply them, this will give you what is known as your area element on the xy plane. Now, if we perform in surface integration here, this will simply cover the area of this circle here, the area of the circle here. Okay, so if you do that like this, integration of the surface dx dy, this will simply be area of the circle. Area of the circle is pi r square. Here in this case, your r value is 1, 1 square. So your result has to be pi, isn't it? So the right hand side, if you understand the problem here, you can directly say that this is actually area of the circle, because we are taking the projection of the by taking a dot product with k cap here, we are taking the projection of this area element whatever on the curved surface over the xy plane. So over the xy plane, the area element is dx into dy, and if you integrate over the surface here, this is simply area of the circle. Okay, but if you have some doubt about it, you can again follow the integration step like I discussed before, by writing equation of the circle on the xy plane as x square plus y square equal to 1, and from here you can take the limit of y from plus to minus 1 minus x square, that is this. Okay, and here you write the element as dx dy, then you integrate from x equal to minus 1 to plus 1. If you follow the same like trigonometric sorry, not trigonometric, calculus here, if you follow these calculation steps, find that eventually you will arrive at this value as pi. Okay, so instead of doing all these mathematical steps also, you can directly write this as an area of a circle of radius 1 pi r square. So but if you do the mathematical step like this, you will arrive at the same value. All right, so then we can verify that the left hand side and the right hand side of this Stokes theorem are both equal to pi. Now I will try to quickly finish this Green's theorem also. So Green's theorem is another vector integration theorem, but here the difference between Green's theorem and Stokes theorem is that in Stokes theorem you can have any irregular surface as long as it is an open surface. Okay, as long as it is an open surface bounded by a closed curve. But in Green's theorem, we are only dealing with planar surface. We only deal with planar surface. If you have a surface on the xy plane bounded by a simple closed curve. So Green's theorem deals with planar or plane surface. Okay. So any simple closed curve, see, simple closed curve means no intersection, which traverse in the positive counterclockwise direction. If m and n are continuous functions of x and y having continuous derivative like this, then this Green's theorem says that loop integration of this m dx plus n dy will be equal to surface integration over the region. This is the region R, but this is a planar region R bounded by this simple closed curve C. So we can have an example here. So this calculation is quite simple, so it will not take much time to explain also. Verify Green's theorem for this, where C is the closed curve of the region bounded by this. Okay. So what is this equation? Y equal to x. Y equal to x means suppose this is your x-axis and this is your y-axis. Y equal to x is simply a straight line. And what will be this angle here? For y equal to x, what will be the angle here? This angle will be 45 degrees, isn't it? Because if x value is 1, y value is 1. If x value is 2, y value is 2. If x value is 0.5, y value is also 0.5. So you will have a straight line subtending an angle of 45 degrees with the x-axis. Okay. Then your y equal to x square. If you draw y equal to x squared curve, it will be something like this. It will go like this. How does it go like this? Below x equal to 1, let's say this is x equal to 1. Below x equal to 1, for example, if x value is 0.1, What will be your y value? Y value will be 0.1 square. This will be 0.01. If your x value is 0.2, your y value will be 0.2 square. That will be 0.04, like that. And when x value is 0.9, your y value will be 0.9 square will be 1.8. When x value is 1, your y value will be 1 square, that is 1. Right. So as you can see in this example, below x equal to 1. So let's say this point is x equal to 1. Below x equal to 1, y equal to x square here. In this equation, y equal to x square here, y value is always less than the y value for y equal to x. Here, for example, let's say here in this case, x value is 0.1. If x value is 0.1, if you draw this equation y equal to x, the corresponding value of y is also 0.1. Okay, the corresponding value of y is also 0.1. But if you take an equation for this, the corresponding value of y will be 0.01. So let's say this is 0.1. 0.01 will be somewhere here, 0.01. So your corresponding value of y is much lower here in this particular equation till this point. But beyond this point, it will still be a straight line. But this curve, y equal to x squared curve, will go like this. So here you are considering a region on the xy plane bounded by the closed curve C, consisting of y equal to x and y equal to x squared. So y equal to x is this straight line, y equal to x squared will be going like this. And the region under consideration here is the one shaded here. The shaded region is what we have to consider, right? So from this, you see that m value is xy plus y squared, n value is x squared. And when we perform loop integration here, you see that this particular, something like this, this is your closed loop, right? But in one loop, this is a closed loop, but in one section of this closed loop from this point to this point here, the equation of that line, that curve is y equal to x squared. But from this point to this point, from this point to this point, the equation here is y equal to x. So in order to perform the loop integration here, we have to split the loop into two sections. That is the first loop C1, the second loop C2. So we are dividing into this, that is y equal to x squared line and y equal to x line, right? So if we have to traverse this curve in a positive direction, anti-clockwise direction, what we have to do is that we have to start moving from this origin and travel along this direction till x equal to 1. And once we reach this point, we have to travel back along the positive along the positive counterclockwise direction. The counterclockwise direction is to travel from this point, that is x equal to 1 here, to travel back here to x equal to 0. So the first curve, the limit is x equal to 0 to 1. The second curve, the limit has to be taken from 1 to 0. So as I was saying, let's say this is your C1. Let's say this is your C2. Along C1, the equation is y equal to x squared. X limit is from 0 to 1. Then you just integrate along Cy. So just by putting the value of y as x squared here everywhere, instead of y, you just put x squared. Here you have a dy. Instead of y, you put x squared. So differentiation of x squared will be 2x. Then you will get 2x cubed here. This is what you will have. And then 2x cubed plus x cubed will be 3x cubed plus x4, x to the power 4 into dx. then you integrate this, then this is what you get, 1 upon this, and this is finally what we have. All right, so that is the first curve. Now the second curve is, as I was just explaining here, we are going from this to this, x equal to 0 to x equal to 1. We are going along this curve C1 to this point, and to travel back in counterclockwise direction, we have to move from x equal to 1 to x equal to 0. So x equal to 1 to x equal to 0, and the equation of this line, is y equal to x. So for every y, you just put y as x, then this is what you will arrive at. If you perform the integration here, this is what you will get. And if you add the two integrations like c1 plus c2 here, you will have this. This is minus of 1 upon 23. And I forgot to display the second part here. The second part, I think you can continue. Everything is, I think, given there in the notes also. Please go through it. The second part is, you just have to take, this is your m is this, your n is this. So what is that? Del n upon del x you have to estimate, del m upon del y you have to estimate. So let me just quickly do it. Del n upon del x will be, what is our n here? X square, right? So del x square upon del x will be 2x. Your del m upon del y will be del upon del y. What is our m here? Our m here is xy minus xy plus y square, xy plus y square. So this will be differentiating with respect to y. You will have this as x plus 2y. Okay, now you have to integrate over this plane as this formula, using this formula. Wait, you have to integrate over this plane, x plus 2y dx dy over the plane. So in order to perform this integration here, we have to use what is called parametric method. I think I've explained there in my notes, so please go through it. So I will stop my lecture now, go through my notes. If you have any clarification needed, you just send me the text, and when I take the next class, I will try to give a explanation to clarify any of your doubt. Okay, so I will stop my lecture now. You can exit the meeting once you type your attendance.